Good afternoon. Today we're continuing with algorithms and data structures. Concretely, that's our third lecture this term. And last week we built more and more complex graph definitions. For example, at the end, we looked at directed weighting graphs that permit loops, and we saw how we can define them. We also saw how we can define them in terms of adjacency matrices. And then we started looking into an algorithm that is called shortest path. And today in the lab, there were quite a few students who had some questions on this on the shortest path, and this is really the right place for you to go if you have questions on details of the shortest path or how to apply it to problems. Come to the lab sessions, and that's where we can discuss it. In essence, the shortest path algorithm has three parameters. We put a start state, a reference to a successors function, and a reference to the isGoal function. And then what this shortest path algorithm does is we think in terms of hops. So going from one state to another. This is not a weighted graph. It's just a graph where we connect the states with each other. And we can go from one state to another in order to solve a problem. We start with a start state, and the isGoal function will return whether a specific state is our goal state. And the successors function generates successors of a state. And we've implemented this algorithm. We discussed it in detail. What is important? We have a frontier. The frontier we also defined, and it contains all non-visited successors of previously visited states. And concretely, we are actually storing not just states in it, but whole paths. And the frontier is sorted by path length. So the leftmost paths are the shortest ones, and we always keep adding to the right end of that list. We also have a set of explored states, because once we have explored a state, we don't want to explore it again. And then we implemented this algorithm and discussed it in detail, and we also applied it to the pouring problem in class, which is also one of the coursework problems. Concretely 7.1, and there were lots of students today in the lab to discuss this, and 7.2 applies the shortest path algorithm to a different problem, which is the missionaries and cannibals problem, in which you need to come up with a new state format. You need to write your own successors function and your isGoal function. And the beauty is, with this approach here, we have separated the search from the actual problem, because we only pass a state that is our start state, the isGoal function reference, and a reference to the successors function. And our shortest path search does not care about the actual state format. So that's a huge advantage. And it's highly generic and can be applied to a lot of shortest path problems. Just by writing your own state format, your successors function, and your isGoal function. One thing that is very important in that I also saw in the lab, if you have a specific problem like the missionaries and cannibals problem, do not touch the shortest path search function. You don't need to amend it, because then it will not be generic anymore. It's generic. Keep it as it is and write your own three elements that we discussed. So don't touch this. So this is the great thing. It's a generic algorithm, and we can apply it to lots of different problems, and we have separated the search from the problem. Because if you try to, for example, solve problem 7.1, the pouring problem, or 7.2, the missionaries and cannibals, and you just try to write this on your own, and what would happen is you would be mixing the search and the actual constraints from your domain, and this would lead to an algorithm that probably does not work, would make debugging and maintenance very difficult, and will definitely not be reusable. So we have generalized it, and it's reusable. So that's what we did in the last week. And today we will slightly extend this. We also saw that there are some other approaches to finding the shortest path, like water and electricity. Did any one of you watch this video on YouTube? It's not relevant for the course, but it's just if you want to learn something new, take a look at it. Maybe send me a thumbs up or thumbs down in case you had a look at this video here. I personally liked the video a lot. So maybe send me some reactions whether you watched it or not. So far, largely, well, some positive responses as well. That's good. I think it's a great video, and I found it very helpful when I saw it a few years ago. Now, we will continue. And as you remember, when we introduced the shortest path algorithm, we said it's an uninformed search algorithm because going from one state to another always has the same cost. It's just one hop from one node to another node in the graph. Today, we will actually work with weighted graphs. So our actions going from one state to another state come with costs. So we don't necessarily want now a path that has the smallest number of hops. Rather, we want to pick the path that has the lowest total cost. And total cost here is meant by aggregating all the costs in your path. And the lowest cost algorithm returns you the path that has the lowest total cost. So since we deal now with a weighted graph, we are dealing with an informed search algorithm because informed means our edges have actual weights, and we want to take that into account. And the lowest cost will find us the shortest path from the start state to the goal state, but in terms of the total cost or aggregated costs per path, as the actions may have different costs. And it turns out programming this is not that difficult, and we will try this now together. And I will open my coding session now, and I'll show you how we can actually implement this. It's fairly similar to what we actually did last week, but with a few changes, and some of them are actually important, or they're all important, but some make a crucial difference. So we can say we're implementing the lowest cost search, and the first three elements are just the same as before. So all we had was start state and references to the successors and isGoal function, but we will have another reference to a function now, which is called the action cost. So a concrete action comes with a cost. And before we said all the actions have the same cost because we just cared about the number of hops in our graph. And I will implement it, and we will later see there are a few tiny differences compared to our shortest path, and we will explore this step by step why we need these differences. What is the same? So we're starting with an empty explored set, but we'll later see how we put something in the explored set. And we are building the same as before, that we have a frontier, and the frontier has a start state, but we're actually putting in the frontier paths. So we're putting a list with the start element in the frontier. And the frontier itself is a list. And we are also checking that we continue as long as there is something in the frontier. And as we did for the shortest path, we take the frontier and we say we pop element 0, which removes the leftmost element in the frontier, which is a path, and it's being returned. And we continue this while as long as there is something in the frontier. And there's one student who asked, why doesn't the explored contain the start initially? I said we're starting now with an empty explored set, and I'll show you later how to add something. And we will contrast the differences step by step. We first start with the algorithm and then contrast the differences. What I need is I'm taking now a path from my frontier, and I want to get the final state in this path. Something we did in the shortest path algorithm was something like this state is path at index -1, which would be perfectly fine, but it's an implementation specific detail. So maybe we introduce a new helper function that we say it's that we want to get the final state of the path, And here we don't care how the path is actually implemented. So it's a small abstraction. Does not make any difference here. We could also just put in path at index -1, but minor difference, but adds a little bit of abstraction. And I'm checking in here now if state 1 is my goal, and if so, I'm returning the path. In our shortest path algorithm, we also had that is goal check. It was moved a little bit, but we are putting it here now in the lowest cost, and we will contrast the differences very soon. So we can check if state 1 is our goal. If so, we're done. We are returning the path. And because this has not happened, we will continue, and we are now adding our state to explored. And since we put it, we can actually wonder what is the total cost of this path? So what's the path cost? And I did not tell you yet how we are storing the action costs in our path. So again, we're adding some abstraction, and I have a new helper function that is called the path cost of the path. And somehow it will be computed. We will later see how to compute this once we have actually looked into what the path will look now. And the next line is just the same as before. We are wondering what are the successors of our current state, and we want the colon, that dictionary, the dot items, which returns us the key value pairs. And we saw before also in the example with the pouring problem that the key is the successor state and the action is the concrete action we are doing. Can be a string, can be something different. And now we're going through these successors, and first we need to check if the state is not in explored, because we don't want to explore something that has been explored before. And now we have our path cost of the path we have so far. And now we're actually calling the action cost function. And we say, well, if I go to one successor of my current state, state 1, I have a state and an action to go there. I need to take a specific action to get to that state. And there could be multiple different actions available here just in the next iteration of that loop. So I need to know what is the action cost of that action. And action cost is a helper is a reference to a function. And we're calling this function action cost and pass an action. Typically, the way you would implement action cost could be, or what we are assuming here, I'm passing an action and I'm returning a concrete value. That would be some real value, could be obviously also an integer, whatever, but we would return some numeric value for the cost of our action. And now we saw this was the total cost up to the current state. Now we're taking another state. So we see we have a new total cost by taking that action, and we can call this total cost is the existing path cost plus the action cost. What you also saw in the shortest path is we are creating a new path that we want to add to our frontier, because our new path is now that we had the old path. So this was this, and we're adding something. But what we are adding is not just an action and state pair as before, but we are adding some tuple to do something and a state. So rather than an action and a state, we are adding the state at the end, plus replacing that action by a tuple itself. And we are storing in there, in this tuple as a sub-element, what is the action we are taking in order to get to the state, and what is the total cost now. And the total cost was the old cost plus the action cost of this action. Now comes one challenge. I need to add my new path to the frontier. Does any one of you have a suggestion without looking at the slides what I should be doing here? How can I add my path to the frontier? And is there anything I need to pay attention to? If you think you know this, maybe just raise your hand or turn on your microphone and share your thoughts with us. We got the right answer already in the chat. One student says it needs to be sorted by the total cost, because total cost, it's absolutely right to sort it by total cost. And by sorting it, we cannot just add this new path to the right end of the frontier because maybe it's not sorted then. So I need to add the new path to the frontier in the right way. And we don't want to spend time, or we don't want to do these details directly in the lowest cost function. So rather, I have a helper function, and I say this is called add to frontier. I'm adding a path to a frontier. And then is still the last thing that can happen. We're there are different ways to terminate this. One way is to terminate by eventually finding a goal, and we are returning this. And if there's no goal, we would run in a situation where this loop comes to an end. And if the loop comes to an end, then we have not found a path. So this was the first draft, and we will discuss this now in greater detail. There's one student who asked, why do we need to sort this? I'll explain it. Overall, this lowest cost looks quite similar to the shortest path. But one big difference is, first of all, we have an action cost. So we don't have the situation where all actions have the same cost, but actions have different costs. So for example, we could say pouring is cheaper than filling. And emptying is maybe most expensive because we don't want to waste anything. So it doesn't necessarily mean that just taking the minimum number of actions gives us the shortest path, but we want the shortest path in terms of the total action cost. And some actions are more expensive than others. So with the old shortest path, we could just append to the right end of the frontier because we said, well, we're just adding one more action, but now actions have different costs. So we actually need to sort the frontier based on the total cost. And we see these paths, they're starting to look more complex. So we don't want to do the sorting directly in here. Rather, we create a helper function and we say, add the path, and I think I made a minor typo. There's in fact a small mistake I just made, I noticed. This one here, and I'll just type it again. This one is obviously not path, it's our new path 2. This is a big difference. It's correct in the slides and in the code I'm providing to you because I've created a new path and I'm adding this to the frontier. If I wrote path here, I would have added the old path. So it's path 2. So I want to add path 2 into the frontier, but at the right spot so that the frontier remains sorted. And it's sorted by the total cost. And that means I'm not necessarily appending this new path 2 to the right end of the frontier, but maybe somewhere I'm putting it somewhere in between or in the middle of the frontier or somewhere in there. And that's why I need to make sure this frontier remains sorted. This is a huge difference. There are some more differences. Something you noticed is this goal test has been moved compared to the shortest path. Why was that moved? If we put the goal test where we had put it in the shortest path, and we studied last week where we put that goal test into the shortest path, was actually further down. What would happen possibly is if we put that goal test somewhere down here where we look into the successors and the actions, we would pick a goal, or if we found a goal, we would have a path, a valid path to the goal, but not necessarily the lowest cost one. Because the path that I find down here has some total cost, but I cannot check it here because if I say, yes, this is the goal, I'm done. But maybe in the next iteration of the successors, or by still popping something else in the frontier, there is maybe a shorter path in terms of the total cost in order to get to the goal. So I need to move this goal check from down here where we had it in the shortest path to up where I'm popping something from the frontier. And when I'm popping a path from the frontier and I have a goal state in there, then I'm guaranteed to have the lowest cost path because I'm always make sure that my frontier is sorted. So if I pop from the very left, I'm actually popping the shortest path in terms of the lowest cost path in terms of the total cost. And then if I do that goal check here, it's guaranteed to give me the right result. And since I've put the goal check here, I don't need to put it in the beginning of the algorithm as well, where it was for the shortest path. So we've moved it up from the inner loop to the outer loop, and then we don't need it in the beginning as well. So these are the differences. And now we got a question here in the chat. One student says, but I'm just reading out to understand what the question is because I haven't fully understood the question yet. So I'll read it out and we'll discuss it. The student writes, but you can't put the goal state in the shortest path algorithm where it is now because there would be no more unnecessary iteration. We're just doing it right and we're actually getting an optimal result because down here, yes, this new path to a successor, and that successor could be a goal, but I cannot evaluate the goal down here. But if I'm evaluating the goal down here, it could lead to a path that is correct, but not the lowest cost path. So I always need to assess when I'm actually taking something from the frontier. And in that moment, I'm taking something that is sorted because there could be some paths, they maybe have 10 more actions than a different path, but in total, the lowest cost because I maybe take more actions, but a lot of low cost actions rather than maybe just a few actions that are high cost. So these are very crucial differences that you need to know. And in the lab, there is no exact problem for the lowest cost. Rather, the lab is meant to be something very free. So what you could think about in a lab is, for example, you could take your, say, pouring problem and you could amend it. So you create one more function for the action cost where you put in an action and you get a numeric value out. And you could call then the lowest cost algorithm. And you could maybe try out, work a bit, experiment with the action costs and say filling is more expensive than emptying and pouring is the cheapest or whatever. Just work with these values and experiment a bit. And then you will probably see that your lowest cost does not necessarily have your lowest cost path does not necessarily have the smallest number of actions, but rather the minimum number of the total cost of all the actions. So this is something you can try out. And I had skipped a few things in here because there are two slides that I had just coded for you. It's the lowest cost search. And you find it here, and please don't copy paste it from the PDF. Rather take it from the resources file in our Nextcloud directory. And what you also find in there are some suggestions how you can implement the path cost and the final state. Path cost and final state are super simple, in fact, because all you're doing with the final state is we take the index -1 of the path, and with the path cost, we just take the correct element from towards the end of the path. And we need a special case in case it's just an initial path where we only had a start state. But this is something you're easily able to implement on your own, so I didn't discuss it here. One thing that is a little bit more tricky is how to add to the frontier. And for this, we are using sorting, but we have not discussed sorting in this course yet. Sorting will come in a couple of weeks. So my suggestion for now is you would just copy paste this function here, how you can add to the frontier. It's at least a very simple approach. It's not necessarily the most efficient approach, but something that takes a few lines of code, but it assumes you know how to do sorting, and sorting is something we'll discuss in a few weeks. So for now, maybe just use this implementation, add to frontier, and feel free to improve it if you wish, because it's not the most efficient one yet. It's just something that works and actually works reliably, and from the performance, it's okay, but can be done better. So this is the lowest cost algorithm. And my advice is, even though there's no specific coursework on it, try to amend your problem 7.1, 7.2 in a way so that you have different action costs. And then you would see, you can run it for a few examples. You can vary the action costs and see what happens. I've mentioned the differences between the lowest cost and the shortest path. I've already explained this. If you want to do a revision, it's just written down what I talked about before. These two algorithms, lowest cost and shortest path, are probably the most generic algorithms that we are discussing in this course because they work on graphs in general. And from now on, we will work on some constrained graphs, be it a list, a tree, a hash table, whatever. They're all graphs, but they come with more constraints and we'll have more specialized algorithms. So these two algorithms are highly generic, and the good thing is you can use them for more than routing, but you can use them in general for state space search problems. So what is written here is also just a revision of why we have built these super generic algorithms, because yes, we want to use them for more than routing. But I've talked about this before. We just have here a revision slide for you. In the literature, you will find numerous of other search algorithms that work on graphs. For example, for routing. One that is also mentioned in the literature is the A-star algorithm. The A-star algorithm is something I will discuss here only very briefly because we've already spent quite some time on the shortest path and lowest cost. However, if you take, for example, an introduction to AI class, which some of you do who are in the AI undergrad programs in German and English, but we also have students from other programs like cybersecurity. They may not have an introduction to AI in their degree program, but the A-star algorithm is something discussed in greater detail if you study, for example, AI. But this is not an AI course, so I'll only briefly mention what A-star is. A-star is also an informed search algorithm, means also works on weighted graphs. And what it wants to do is it expands the path which has the minimum value f. So our paths, they have not now a total cost, but they have some value f, or say they have some cost, and we want to pick the one that has the minimum value. And A-star is a so-called heuristic algorithm because we try to estimate some of the costs. And concretely, our F is composed of two components, G and H. G is the current cost of our path. So we have a path up to where we are now, and we have a cost that we needed to spend to make it there. And now we wonder, how much cost do we have left in order to get to the goal? And this is something we need to estimate. And that's why it's called H, and H stands for heuristic, because we have a heuristic algorithm that estimates the distance to the goal from our current state. And then we sum up G and H, which gives us F, and F is that minimum value, or F is something we calculate for the different paths, and we pick the path for which we have the minimum value F. So H is a heuristic function. And A star relies a lot on this heuristic function, and the A star finds or is guaranteed to find the lowest cost path if the heuristic value of S, our current state, is less than or equal to the true cost. What does that mean? We need to have some sense in our estimation, and we can underestimate the cost. So the heuristic is allowed to be less than the true cost, or less than or equal to, but we are never allowed to overestimate the cost. This is something very important when we build the heuristic for a specific problem. But we can underestimate, that's fine. So our age never overestimates. We can always estimate exactly, but we're also allowed to underestimate. And this is something that we say that age, this heuristic function, is optimistic or admissible. Optimistic makes sense because we're allowed to underestimate the cost, but we're not overestimating. So this is something that makes sense to me that we can call it optimistic. And there's one example here. It's a small example world. So imagine we have our start state where we are right now, and we have a goal. And we want to know how many steps it would take in order to get from S to G. Right now, we're using this A star in a slightly simplified way because each action is just one hop. So it's not like that moving down is more expensive than moving up, but you can customize this A star obviously also to more generic problems, maybe not just such a small sample world, but something that we have done before. For example, with the, say, the pouring problem or the missionaries or cannibals or some other optimization problem. And what I have here on the right is the heuristic. And the heuristic estimates what's the distance in terms of hops that I need to take in order to get from one state to another. So for example, down here is a 0 because we are already in the goal. So I don't need to make any other steps. Here's a 1 because I need one more step. That's what the estimation says. Here, 2 more steps, 3 more steps. And from up here, 9 more steps. Do you think this is a valid heuristic? Is it optimistic? Maybe green sticker or thumbs up if you think this is valid, or thumbs down or red sticker if you think this is not optimistic. And maybe some more responses. One student said red, thinks this is not a valid heuristic. Maybe do you want to tell us why you think it's not valid? Now we have had a few positive responses. And the positive response is actually correct because we never overestimate the cost. We estimate it actually perfectly, but we said the heuristic must be less than or equal to the exact value. So it's a less than or equal to. And in fact, we're just perfectly estimating the true cost, which is fine. So it's the equal because it's 9 hops from down here. What would happen if I put in a 2 in here? Would this be a valid heuristic or not? If I put in a 2 in here instead of the 3, send me a green sticker or red sticker. Green means it's still valid, red means it's not valid. And maybe some more responses. It's almost split the responses, just a minor difference. Who of you wants to argue? Turn on your mic or your chat and tell us if you think if this is fine or not. One student already responded and says we don't overestimate, so it's fine, and that's correct. I can put in a 2, it underestimates, but that's okay. What happens if I put a 10 in here? Is it still valid or not? If you think it's valid, green sticker. It's not valid, red sticker. So only red responses, that's correct. It's not a valid heuristic anymore. So this is just a brief overview since we're now at the end of the graph chapter. A star would be discussed in greater detail in an introduction to AI course, or maybe if you take a course that is only on graphs, this is the kind of stuff that may be discussed. But we are in this course, we are more interested in the lowest cost and the shortest path. And from now on, we will actually keep working on graphs, but we constrain them and we have more specialized algorithms. This chapter still contains a few best practices. Something that I have noticed throughout my career is a lot of algorithm problems, not all, but a lot of algorithm problems are in fact some kind of graph search problem. And a lot of problems, in fact, are something for which you can, like optimization problems, you can use this shortest path or lowest cost for. So if you see some problem that fits into this category, try using these algorithms, try amending, or try writing your own state format, your successors function, your is goal, maybe your action function or action cost function, and try to reuse these implementations. Later in this course, when we see some other data structures, we will actually think about how we can improve the shortest path and the lowest cost. And obviously, there are also a lot of optimization problems for which maybe these very generic algorithms are not that helpful, but maybe you can build something more specialized to take advantage of some inherent structure in a problem to optimize further. But yet, you will see quite some problems in your career for which these two algorithms here in this generic state search are probably quite helpful. So don't reinvent this. And if you have a problem of that sort, you can apply this also to, I don't know, going through a maze from the entry to the exit. Don't try building your own algorithm. Reuse our shortest path or lowest cost, probably shortest path, and write your state format, your successors function, and your is goal function. But something I also noticed is throughout my career, a lot of problems in computer science or in industry also are often graph problems. Because when we deal with data, we have some kind of data structure, and maybe this is some kind of graph, maybe a very constrained graph. But it turns out a lot of problems we try to solve are graph problems. And maybe there's already an algorithm for your problem. And there are great books about algorithms. I have lots of algorithm books at home, lots of famous books. But buying all of them to look it up, I know is expensive. And on Wikipedia, there's a very, very nice list. It's a list of graph algorithms. There's an article on the list of algorithms. And in fact, there is a huge list or a huge sub list on graph algorithms. It doesn't mean that all these Wikipedia articles are great for the individual algorithms, but I like the list, the collection of all these algorithms. And then you can study these algorithms either from Wikipedia or from a book, but these lists are quite comprehensive. So look that up. And throughout my career, I've also noticed that some problems that seemed extremely challenging, in fact, they could be generalized and could be seen from a graph problem. And then maybe there were already some graph algorithms out there in the literature that I could use or amend. I had a experience like this when I was a little bit older than you, when I was in my fourth semester. So most of you are now in your second semester. So I was 1 year ahead. I had my mandatory internship at a very large software company, concretely SAP. And the team I was in, they built software for transforming data for so-called mergers and acquisitions, or for currency conversions, or for major transformations of an SAP system. They built transformation software for that. So, for example, a merger and acquisition would be you're buying a plant, you're selling a subsidiary, or stuff like this. This is something you cannot just click in an SAP system. Rather, you need consulting projects for this, and the consultants need special software to convert the data. And we built that kind of software. And the team was facing in one of these software products or one of these tools some algorithm problem that the team had looked into for years and they were never really able to fully fix it. So there was some problem and they always customized the code. And for one consulting project, they set some flags or changed some thresholds and stuff like this. But they weren't able to solve this problem from a generic perspective. What the problem was exactly doesn't matter here. But I was then there as a fourth semester, so at the end of my second year as an intern, and they told me about this problem, and the team had looked into it for a long time, and they always made some hacks here and there for another project, but then these hacks had to be changed for a different consulting project, so for a different database of customers, and they just, it was a lot of trial and error in order to make this work. And then I looked into it. And I did not know how to solve it, but at some point I noticed that this was actually a craft problem because the team did not see this as a craft problem. It was a data transformation thing, but I saw it as a craft problem. And then I didn't know how to solve this craft problem, but I actually looked up what craft algorithms are out there because I felt I had seen some craft algorithm that could do partially the work. And concretely, it was topological sorting. Topological sorting is an algorithm that brings order into dependencies and in a way in a directed graph. And I had heard about that algorithm, but didn't fully remember it or didn't fully study it in detail at that time. And then I looked it up and saw, well, the topological sorting is actually what I need. But that's maybe 30 lines of code if you implement it, or even less in Python. And I felt, well, the topological sorting is not solving my problem, but it's going somewhat in the right direction. And then I implemented the topological sorting, which was 30 lines of code, but then I had to add a lot of business rules for this kind of problem, for this kind of data transformation problem, which was maybe, I don't know, 1,000 lines of code on top to build these business rules that the team was facing, and made some strange, or from my perspective now, there's some strange changes to the topological sorting, but then it worked. I coded this maybe within 1 or 2 weeks and tested it and included all the business rules. And it turned out that that amendment of the topological sorting solved that problem that team was facing very well. And it solved it in a generic perspective. So the algorithm did not need to be minorly changed again for a different database. Rather, it worked because the setting in which we dealt and the business rules, this was always the same. So I was the one who saw this as a craft problem and solved it. And I was running and didn't need to be amended anymore. So you see, you are able also as a student to contribute something useful to companies, even to very large corporate, if you have some good ideas. And that's why when you face some algorithm problem, maybe sometimes it's a craft problem, look up what kind of existing craft algorithms are there. There are lots of them. Maybe use them, amend them, or get inspired by them, or combine them. You can solve lots of problems with that. So these are my best practices on crafts. And now we've done crafts, and we'll do lots of more constrained crafts, lists, trees, maps, and hash tables, and other data structures, especially lots of variations of lists. And these are all crafts, but some kind of graph with constraints. And we will explore these algorithms. We want to see how to build lists, how to manipulate lists, how to manipulate trees and hash tables and compare all of them. And for this, we need to be able to compare how efficient our algorithms are when we work on these data structures. And in order to assess how efficient algorithms are, we need a framework that is called complexity analysis. First of all, we start with time measurements. We will measure how long it takes to run an algorithm. We will then look into complexity analysis, lots of different notations, which all look into time, into running time. But in an algorithm, you not only have running time, but you also have memory usage. And memory here means RAM, so main memory. So we can apply our complexity framework also to space, meaning to memory usage of an algorithm, not just to time. This will take a little bit to develop this framework. And first of all, let's start with a question. How long does it take to run some algorithm? So you have some algorithm, you have some function that runs in Python, and you want to determine, without complexity, just the running time, how many seconds or milliseconds does this take? Does any one of you know how to determine this in Python or Java or some other language? Maybe thumbs up or green sticker if you have ever seen something like this or try to measure how long it takes. You could obviously sit there with your phone and try to measure the time, but that's probably not very exact. So there are a few positive responses. Maybe you want to turn on your mic and tell us how you would determine something like this. Or send it in the chat if you don't want to turn on your mic. Let's see if anyone is responding. It's your course, your discussion. One person says, we need to work with the system time, milliseconds. One person has done this in Java. Good. One person says they compared strings and string builders and then probably measured the time, how long this takes. Good. We need to do this in Python too. We need to measure now how long it takes to run something. So let's say we have an algorithm. So def algorithm. And the algorithm does something. For example, it's just a loop. Like, for example, we have a result, which is 1, and then we have a range of 1000, and we multiply this result with I. It even doesn't return anything. It just computes something. We don't care about what's being returned. So it's some algorithm. I can run the algorithm, and we see it seems to complete almost instantaneously. Yet maybe it could take 50 milliseconds. I don't know. And if we make this integer larger, it will take ever longer. So we could also change this to 10,000. So we want to do 10,000 multiplications. Also still runs fast. So what we need to do now is we need a function that is called time, because from the time module, we have imported a time, and this returns us something. I have called time, and I will call it again. Here in the Python world, it does not return milliseconds, but rather seconds, but as a float value. And this is a large number of seconds. And in fact, this is the number of seconds since a reference date. And the reference date in most operating systems and programming languages that we use nowadays is January the 1st in 1970 at midnight, using the UTC as a time zone. So we see that time keeps running. And now I want to run my algorithm, and I could try to measure this. So I could say, I want my start time is the time. Then I run the algorithm. And now I want to know the end time, it's the time. And what I can try is, well, end time has grown compared to the start time. Then I get something like 7.7 seconds. This doesn't look right. Now, the system claims, or we may assume, it took 7 seconds to run this algorithm, which obviously did not take 7 seconds. Any one of you has an idea what I did wrong? Maybe thumbs up or raise your hand if you see what I may have done wrong that the computer suddenly claims it took 7 seconds to run this. If you have no idea, maybe red sticker or something. One person, Green, do you want to turn on your mic and tell us what I did wrong in this measurement?
Yeah, you should have run 3 lines together.
Exactly. Thank you very much. That's perfect because I ran one line and it's the interactive mode, and then I had to type the next line and the next line. So the typing also took time, and the time passed until I had typed and executed this statement. If you run this in a Python script, so in batch in your IDE, for example, it's fine. This will work. But in the interactive mode, it will not work because the interactive mode runs this command or runs this per statement. So I need to run these three statements together. So in one block. If you use the Jupyter notebook in the browser, this would be one code block. And here you can do this too in your IPython. You can say, well, I want the start time. And then you need to press on your, if you use the terminal, you need to press and hold Control and press O. So Control O will add you two more lines, and we are running this together. So then we run the algorithm, and then we run the end time. And then this is run together, or obviously not in parallel. First the first line, then the next one, and then the next line. It doesn't wait for us to type it in. And then we can calculate this again, and we see, well, this took like 0.4 milliseconds to run, in fact. So fairly quick to do the 10,000 multiplications. So when you run this in batch, say in a script file, you can just run it this way. If you run it in your interactive environment, make sure you run these statements together in one block so that you're not biasing your measurement by with the waiting times for typing and so forth. Something very important. So this is how we can measure how long it takes to run some code. And here's just the same example that I've just typed. We are running some algorithm. So we're measuring the execution time. Now, if you run some algorithm on your computer, it takes maybe 10 seconds. So if you run it on a different computer, it runs 5 seconds. If you run it again on your computer, it may take 8 seconds. All of this can happen. So we see comparing running time is actually quite difficult because maybe one of you just has a faster computer, or maybe your computer was busy with some other stuff in the background. So comparing just these running times is not very helpful unless you run these experiments on exactly the same hardware and exactly the same software environments. Because maybe just a new version of Python makes it faster or slower. So this is one challenge. And when we do such running time experiments, say we have an algorithm that depends on some input. It would does work on an input, and maybe the input is more complex or longer than a different input. So you would run your experiments on some number, some limited number of test inputs. And which ones do you pick is another question. And maybe so far your algorithm is just pseudocode on a piece of paper. But now in order to run it, you need to implement it and then measure the running time experimentally. But maybe you just have a concept on a piece of paper that you don't want to run yet, but you want to assess it. And there's lots of other stuff that can bias your running time measurement. So which hardware do you use? Which CPU, number of cores, caches, RAM, which operating system do you use? May make a difference. What else are you running in the background? how many other processes and threads are you running in the background? Maybe thousands of other threads are running in the background. And then your operating system uses scheduler to assign running time to processes and threads. Depending on how the scheduler works and what's running in the background, this may be running faster or quicker. Then there is swapping, meaning you run out of RAM and some of the RAM is stored on your hard disk or now your solid state drive, something that is much slower than your RAM. Then you have caches, and sometimes the cache may be already filled with the values you're looking for, sometimes not. So all of this has impact on your running time measurements. And that's why these running time measurements, they're not very helpful. Sometimes they may be, because sometimes we really want to serve something that takes less than a second or less than half a second for a certain customer. But this is maybe something more like a consequence, something we would do at the end. But rather, we want to design algorithms that are efficient without running measurements all the time. And something that can happen here is, say we have some algorithm that does something like sorting some numbers. And we have the input size, or maybe not numbers, but sorting some sophisticated objects, which takes some time. And we can have inputs in terms of thousands. So each tick is 1,000. And we see if we put in like 1,300 elements, this takes about 80 milliseconds. But if we put in, say, 3,000 and we run the experiment multiple times, say with the same input, sometimes this takes 50 milliseconds, sometimes 90, maybe sometimes 140. Or we put in the same number of elements in our inputs, but they are different inputs, different objects. They are varying, so this may lead to this spread. So what we see in here is a positive trend. That means more running time is needed when the inputs get bigger, yet there's quite some spread in here, as we can see. So this is actually not very reliable, but it's a start. So we need something totally different. We need a new approach for determining how efficient or how inefficient an algorithm is. And our new approach will use mathematics now, and we will actually look into complexity theory or complexity analysis. What we want to do is we want to be able to compare two algorithms and their efficiency totally independent of hardware and software. All we need are high-level descriptions of the algorithms. We even don't need to implement them in code. And we can take into account all possible inputs and make some determination for when an algorithm is more efficient than another one. And we're now building a theoretical framework for this. And this framework consists of multiple parts. One part is we will think in terms of so-called primitive operations, which are simple operations in an algorithm. Something we will see very soon. And we want to have, from now on, when we look at an algorithm, we will just see that algorithm as a function of the size of the input. Say we're sorting something or we are searching in a data set. We are putting in some input, some input in the algorithm that has a certain size. And we actually want to count the number of primitive operations. We don't later want the exact count, but we want to see how that number of primitive operations that the algorithm needs, how that changes and how it depends on the input size, and how quickly that order of primitive operations is growing based on the input size. Some algorithms may grow very, very slowly in terms of their running time. Some may grow very, very quickly. And rather than thinking about concrete inputs, like we're not measuring individual or a sample of inputs, but rather we will focus on the worst case input we could put into that algorithm in terms of its complexity. And these are the three core principles we're discussing now in greater detail. And once we have done this, we will glue it all together and we will start analyzing algorithms and their number of primitive operations. So we will look into primitive operations. This is something I said are very simple operations. And the primitive operation corresponds to low-level instructions in your code. For example, assigning some value to an object or variable, doing some arithmetic operation, like a plus minus, a multiplication, a division, whatever, or comparing two numbers, using a Python list and accessing an element by an index. So index 0, index 100, index 5000, or calling a function, but this means only the function call, not what the function actually runs, because there are more operations, or returning something from a function, or an if-else, stuff like this. So these are some examples for primitive operations. And obviously, some primitive operations are more complex than others. Like a division is maybe more challenging than an addition. And assigning a value to a variable is easier than comparing two numbers. But this does not matter for us. And this is a theoretical framework. And in our framework, we just say, well, we have these primitive operations, and we assume more or less each primitive operation takes more or less the same running time. Obviously, in reality, maybe comparing two numbers is more difficult, or comparing two very large numbers is more difficult than comparing two very small numbers. But it doesn't matter for now. We just care about primitive operations, and we simply want functions that depend, for which the number of primitive operations depends on the input size. And we assume each primitive operation just takes exactly the same amount of time. And we don't care about that maybe one computer is a bit faster or slower. Maybe one computer can run a multiplication a little bit faster than a different one. We don't care about this. So we just assume that the running times will be fairly similar of these primitive operations. And we will now look into a function f that represents our algorithm, but the function f has an input n, and n is the input size, so the size of the input. Maybe a list has 5,000 entries or whatever, or a tree with a certain number of n nodes. And this function f will mean now how many primitive operations the algorithm needs depending on the input size. And it makes sense if I want to sort a list that has 5,000 entries, this will obviously take longer than a list that has 10,000 entries, because there will be more primitive operations. But how much does the number of primitive operations grow based on n? That's the question we want to address. And building these functions f of n may sound very complex, but in fact, it's not that complex, because we can compose it of basis functions. And we will look at these basis functions very soon. And what we also said is, so we said we look at the number of primitive operations, we see how f of n, the number of primitive operations, depends on n. And I said we always assume the worst case input. For example, the worst case input could be a totally unsorted data set, and we want to bring in structure. The best case input would be that the data structures may be already sorted and I don't need to sort it anymore. But we always focus now on the worst case input, whatever it could be, depending on our algorithm. And the algorithm may run faster on some inputs and worse on others that are the same size, because maybe a totally unsorted data set takes longer to sort than a sorted one. Maybe, but we will see there are exceptions to this rule when we look at sorting algorithms in a few weeks. So we will look always now into the worst case input and see how does the number of primitive operations develop based on when I increase n, the input size, and I put in the worst case inputs. We could obviously think about a distribution of possible inputs, like which ones are more likely to come into the algorithm, which ones are totally unlikely. And we could try to think about some average analysis, but these average analysis are quite tricky because you would need to find a probability distribution of the set of inputs. So we always optimize for the worst case. And just as an example here, say I have some algorithm that does something, and running this algorithm takes a certain number of milliseconds, and I have different inputs. And I see for some inputs, it runs fast. For some inputs, it takes longer. And we would always, and we assume here, just to clarify this, that these inputs, they all have the same length. So it's not like one input is longer than the other. But this input here, dealing with A, is slower than dealing with E, because maybe A is more complex, has the same size than E, but is maybe more complex to sort than E, because E is maybe already largely sorted. So we could think about the best case, we can think about the worst case, but the average case is quite tricky because we would need to find this probability distribution, which is tricky. So rather, from now on, we say we always care about the worst case input and we optimize for the worst case input, because this is actually far easier from the analysis than an average analysis. And we will optimize for the worst case input. And this approach typically leads to better algorithms if we focus on the worst case input. And typically, once we have built a very good algorithm, an efficient algorithm for the worst case, such algorithms tend to perform very well on every input. There are exceptions, and sometimes you need some special cases. But for most cases, probably when we optimize for the worst case, it will perform well on every or nearly every input. And I said we want to build f of n. And f of n will be built now with basis functions. And we'll look at a number of basis functions. We look at them very, very quickly because these functions are something you have definitely seen or you know them from high school and their rules. But we start with the constant function. So f of n is a constant c. And the constant is some value. Can be 5, can be 27, can be 2 to the 10, or can be 10 million. But we see that c is independent of n. So the algorithm will always need c many constant operations, no matter what n is. So that would be a constant function. And the constant one could be, for example, just an assignment. We assign something or we return something. We don't compute it, but we just assign it, we return it, whatever. That could be maybe constant. And it turns out, obviously, it takes longer to run 2 to the 10 many primitive operations. This takes far longer than running 5 of them. So you need to run, say, 1024 assignments in your code of values. This takes longer than if you do it 5 times. But in our framework, all we care about is that f of n is independent of n because z is independent of n. And we don't care in this framework about the exact value of the constant. Obviously, in running time, it makes a difference if you run a billion primitive operations or just one. But in our framework, we only care about how the number of primitive operations will develop based on when we change n. And because some computers are maybe more parallel than others to run this constant many operations just much faster than others because of a different CPU or an instruction set, we typically tend to ignore these constants. Obviously, the constants have impact on the running time, but not on how the running time develops when we make n larger. So bear that in mind. So this is the simplest function, a constant function where the constant value does not depend on n. Then we have the logarithm function. And you've seen all of these functions that we look at now in before and also in high school. We can say f of n is the log b of n. And the b is the base constant of the logarithm. For example, binary logarithm. Typically, if we don't define b, we just say b is 10, and then it's the logarithm with base is 10. So you take the log 10 of 1000, which is 3, because 10 to the 3 is 1000. But we can vary b, but b is a constant. In computer science, oftentimes, we don't deal with logarithms to the basis of 10, but rather with binary logarithms, because in computers, we deal with binary. So often we deal with the binary logarithm. So in this course, if we don't define the basis, we don't typically mean 10, rather we mean 2, because this is a computer science course and not a math course. But again, it doesn't really matter, because log b of n is the variable, b is the constant, and we can just compute this as the log n divided by log b. And if n is the variable, but b is the constant, then log b is a constant, and we ignore constants, as you heard before, because we don't care really too much about constants in our framework. That's why the basis doesn't matter too much, and the log b of n, all we care about is that it has a logarithm development, and the exact number of steps, we don't care. There are all sorts of logarithm rules, like the log b of the product of a, c is the log b of a plus the log b of c. I'm not repeating these logarithm rules because you have all seen them in school. And if you haven't seen them, please revise them. They're important. If we want to search in a data set, for example, we would think maybe we have to go through all the entries to find something in the worst case. So we could think it takes maybe linear time to go through a data set to find something, assuming the data set is not sorted. So we would say f of n is n, because when n grows, searching, or the time you need for searching in n, also grows, but linearly. And this would be a very simple search algorithm in a list. And later in this course, in a few weeks, we will see it's not necessarily always linear. Maybe our data set is sorted, and then it turns out we can search in logarithm time in a data set. But this is something we will see. Just to bring in some examples. And f of n is a linear function. Sometimes there are also constants, like f of n is 10n. But because we ignore constants in our framework, all we care about is that the number of primitive operations, f of n, depends on n linearly. So when n grows, f of n grows linearly. And this would be, for example, much better than n squared, because n squared would be growing quadratically. So the number of primitive operations grows much faster than for a linear one. Then this is the quadratic function I just mentioned. N squared is n times n. So when n grows, n squared grows much quicker. N squared could be, or let's start with n. An algorithm that is in the order of n could be, for example, a loop. So we have a loop iterating over our data set. And when the input list, for example, gets larger, then we need more iterations in our loop to go through it. So it takes more time. But sometimes you have a loop within a loop, for example. And a loop within a loop where both of the indexes depend on the input size, this would actually be n squared much time. We will see all of these examples in the coming weeks. Some examples maybe today already, depending on how quickly we progress. But a loop within a loop, this could be, for example, quadratic time, where we need a number of primitive operations that depends on n squared. Then there is a different function that is called n log n. So I have n and I multiply this with log n. N log n grows faster than n because log n will be positive as n advances. But n log n grows much slower than n squared. So maybe for some problems, especially in sorting, there are some sorting algorithms that need n squared much time and some that need n log n time. And then we very much prefer the n log n one because it runs much, much faster and we need much less primitive operations than in n squared. And there are much more basis functions that we may need when we study our algorithms. One of them is, for example, f of n is n to the third, or more complex polynomials, which could be f of n is a0, which is a constant, then constant a1 times n, constant a2 times n squared, plus constant a3 times n to the third, plus, constant ad of n to the d. Which of these terms contributes the most? So we assume now n gets very, very large. And d could be, for example, d to the 10, just as an example. So which of these subterms contributes far most to the count of f of n when n gets large? Which of these terms? Maybe send this in the chat or turn on your mic if you want to share with us which of these terms largely contributes the most to the value of f of n when n gets larger.
The last one.
Exactly. AD times n to the d. And in fact, it's also the n to the d because AD is a constant. Some constant can be 100, can be 1, can be 10, but we said we don't care much about constants. What we care about is this part here in the polynomial, so the highest order one. There are some example polynomials that we can generate from this generic definition. And the next function that is a basis function is the exponential function. So the exponential function is f of n, the number of primitive operations in the algorithm is b to the n. So where we depend, where b is the constant and the power is the variable. And this grows far quicker than all the other functions we have seen before, provided n gets big. And in computer science, the base is b. This is the constant for which we typically assign 2 in computer science because we deal with binary. Sometimes there are obviously other constants. And there are, again, some exponent rules that you need to be familiar with. There are this is an interesting plot. What it is, you can look at it and see how the x-axis and the y-axis develop in each tick. So this is 10 to the 1, 10, 10 to the 2 is 100, 10 to the 3 is 1,000, 10,000, and so forth. And we also have a different value per tick in the y-axis, 10 to the 4, 10 to the 8, 10 to the 12. What this plot is helpful for, it allows us to visualize these functions a little bit better as n grows. And we see the one that grows the quickest, it's the one with this dot, it's the exponential function. And we see, for example, this one here grows very, very slow. It's the logarithm function. So when n gets very, very large, it grows very little. This was the logarithm. Above it, we have the linear function. Slightly above the linear function are these squares. This is the n log n function, which grows a little bit faster than n, but still much slower than quadratic. And up here, this is cubic. So this kind of plot, just with what we assign, the values we assign to these ticks, helps us to visualize these growth rates for our fundamental functions quite well, even when n gets large. So let's dig deeper into the core principles of our framework. All we want to know is how the running time of an algorithm grows proportionally to n. We don't want to know the exact number of primitive operations. We only want to know the order in which the primitive operations grow based on n. When n gets larger, does it grow linear? Does it grow logarithm? Does it grow cubed or exponential? That's what we care about. And we will analyze our algorithms using a mathematical notation in which we just ignore constant factors. And in fact, we will also ignore the lower order terms. We always will focus on the largest order term because this is the most significant one contributing to the number of primitive operations as n gets big. And we can apply this to pseudocode, so we don't need to implement the code. We can implement it, obviously, but maybe sometimes you just have a concept and you haven't implemented it yet. And we will be able, with our framework that we establish now and use everything we have discussed so far, we will be able to estimate the number of primitive operations of our algorithm, or at least the order in which it grows. And then we would tend to pick the algorithm that has the best complexity. So the lowest order one that does our task, that's the one that tends to have the lowest number of primitive operations. That's the one we prefer. There are exceptions, obviously, and we'll have lots of time to talk about these exceptions. But we will come now to a quick coding problem. And what I want to know is I want to implement, so I have a data set. So I have a data set of values 1, 5, 2, 9, 100, -4, and 10. And I want to find the maximum value in here. This is, I think, also one of the coursework problems in the Python primer. I want to have a function that is called findMax. I pass my data, and I want to return the largest value. So I want to return largest value. How do I find the largest value? I can say I look into the first element, so index 0, and then I go through all the values in my data. It's not working perfectly fine. It's just a simple approach. It can be done better, obviously. One student suggested finding the maximum value is we can sort the data set and then return the last element with the greatest index. That's fine, but we don't know yet how to sort. This is something we will establish later. What we can do now is we say, well, we have this helper variable largest, we assign the first value to largest, and then we go through all the data step by step with a loop, and we can say if our current value is larger than the largest value, then the largest value is my value. Let's run it on findMax on let's run findMax on the data set, and we get 100. What do you think about this implementation? Does it always work? Does it have some downsides? If you think it looks fine, maybe thumbs up. If you don't like it, if you see some shortcoming, maybe thumbs down. So one student is happy, all students are happy. It works almost. Something can go wrong. Imagine I pass a list with one entry. Then it works. It finds this value. But imagine I pass an empty list. Then I get an exception because I'm indexing and I'm checking at index 0, but there is no index 0 because it's empty. So this does not work. So this is an algorithms and data structures course. What you will often see in our algorithms is that maybe we don't care too much about some corner cases, some edge cases. Like, obviously, if you write this proper in software engineering, you would need to add something like and check if the length of the data is 0, then we would do something, maybe return an exception, raise an exception or something, but it's nothing we care about here. We just assume, like one student says, we could return none, we could raise an exception. There are lots of stuff we can do. Typically, we would raise an exception because it's just invalid. But we're ignoring this. One student also suggested, well, we are starting then here again with index 0. So we check the first element again. We could start with the second element. That's also correct. But it's just a very simple implementation. And I want to know from you, where do you think the algorithm spends most of its time on? In which of these lines do you think? So this one here is line 1, line 2, 3, 4, 5, 6 lines. What do you think in which area the algorithm spends the most time on it? One student says when we do this comparison, okay. Line 3, one student says around the loop. Okay, maybe then tell me the opposite. What do you think is where do I spend very little time in this algorithm when the data set gets very large? So we assume always large data sets, worst case inputs. And worst case here means the data is not sorted because the best case could be it's sorted and I just need to pick the last one. So once some students say we spend very little time in here in returning an integer. Yes, that's true. We also spend a little bit more time, but little time here because we have one primitive operation for indexing and then for assigning this. So we actually have two primitive operations. We have one here, but actually we're spending most of the time somewhere in this loop. And there is a notation that we will introduce very soon. And we can say we need time in the order of something. So it's a big O in the order of one. And the one is a constant. Actually, we need two primitive operations here, but we just say in the order of one. So just constant time. We also need constant time down here. But when we do this loop, we actually need n much time because the loop will run n many times, where n is the size of this list. And in the loop, we again have primitive operations because this comparison is primitive and the assignment happens sometimes, sometimes not, because we sometimes may get into this line, sometimes not. But actually, the loop, whatever happens in the loop, contributes the most to our running time when we run this many times. Running many times means the loop for a large data set. So we see with our algorithm, the simple algorithm here grows proportionally to n, the running time, as the loop executes once for each data element. So the beginning is very simple, the end is very simple, but the loop actually contributes the most, whatever happens in the loop. And also here, something is done because we pick one element from data, we assign it to value, and these are also primitive operations. Next week, we will look in the so-called big O notation because we had just seen these big O's. And next week, we will look at what they mean. And we are introducing this big O notation. If you look at the coursework, there is lots of coursework on the complexity analysis. We are just at the very, very beginning, and we have not introduced the O notation yet. So there will be very little to do in the complexity analysis so far, because we need next week's lecture to introduce the O notation. But since in the last two lectures, we already spent half an hour extra today, I want to finish on time. So if you still need time in the coursework to work on these problems from graphs, take the time. If you still need time to study Python more, take that time. If you have done the work on the graphs, maybe work on the mandatory problem, because the mandatory problem is about the pattern matching algorithms, which are explained in the book, and you need to implement them and run them on some sample data sets. So if you're okay with graphs and that you're done with the coursework on graphs, take a look at the mandatory problem. There will not be much for you yet in the complexity analysis. We'll only be able to do this after next week's lecture, because in the next week lecture, we introduce this O notation. But what you should take home as a revision is we think in terms of the primitive operations. We have these basis functions. Familiarize yourself with them and the rules and how to manipulate them in case you're not familiar with this anymore. And next week, we will look at this big O notation, which helps us, which we have already used here without understanding what it is. And we will introduce it, we will apply it to algorithms, and we will introduce a couple of other notations. And then we have all the tools available to compare algorithms based on their complexity. And complexity is a measure of how the running time, as the number of primitive operations grows based on when the input size gets larger. Are there any questions for the end today? If you're all okay, send some positive response. If you want me to wait in the chat, send some different response, and I'll wait here in the chat. So today we're finishing on time. I wish you a good weekend and see you next week in the lab and in a lecture. Take care. Bye-bye.